All right, we're back. We are comp game 2005, game 2005. We okay. In the fall 2017 semester, and it's week 6, part 2 of our broadcast. We did part 1 on Tuesday. It is Thursday, and we're kind of in the lab session. We're still talking about 2D motion with Unity. What I've done is I've put up a little project for you guys that I worked on with the other team. All right, so the first group, who are my guinea pigs. If you go to GitHub, and it's on GitHub / George Brown College. George Brown College, that's the GitHub link. You'll notice that there should be a link, but there's not. Where did it go? That's okay, I'll put it up in a second. George Brown College. And then let's see, maybe it went on to my regular account, which would be very bad. But yeah, I could always fork it for you guys. Did I? Yeah. Chances are I did. Yeah. So I'll put it on my. I'll just duplicate this on George Brown College. Just give me 1 second while I do that, as I work through all these kinks. All right. So I want to create a repository up online. I'm going to make a new repository here. Game 2005, and it's the fall 2017 semester, and we're just going to call it lesson 6. And why is, oh yeah, because it's his. See what it's trying to do? George Brown. There we go. That would work. And there we go. All right, so that's going to be the repository. It's empty right now, but I have my files that we were using before. I'm just going to kind of drop all this stuff for a second now. Unfortunately, I have to, whenever you do stuff with Unity, for those people who don't know, you need to close it, or else when you put it up, you put the repo up, it just will not capture everything, which would be bad, right? So that's why we're going to put it up. So there's my Unity. I'm going to go into command line here to do this. So GitHub won't be a requirement. It'll be just your code, but it'd be nice to have. So I'm going to say CD. It doesn't matter whether you're a Mac or Windows person. It works the exact same way, right? I need to delete my repository, my my local repo. So I'm going to say rm-rf.git. And then I'll just initialize the repository again. And then I'll put an initial commit up where you guys can see what I have. And I already have my repository made, which we just did together. This one. So let's grab these last 2 lines of code and commands and put them in, and then that will be up. So you should have access to it right now. Okay, so if you want to download that project, you can go ahead. But that's where I'm going to be working with today, this little code. I wish I had a bigger chair. With Unity, there's advantages and disadvantages that we saw when I was with you on Tuesday. One of the advantages with Unity is that it is a quick setup. One of the disadvantages with Unity is it's a quick setup, and you don't know what the hell you're doing, right? You don't know what's really going on in the background. And you have to adhere to a particular pattern. It's a framework, right? A game engine, and turning certain things off or manipulating the game engine to make it do what you want it to do by turning off features is not as easy as it looks. I'm going to end this scene number 2. We started off with one scene and the main scene, and I've kind of moved on to scene number 2. And I want to talk about some of the scripts I wrote. So scene number 2, it looks pretty basic. I mean, I have this little game, right, that I created. It's not really a game, but if I go to the ball controller, this is where all the logic comes into play. And this is what we were struggling with on the Tuesday. So I want to kind of share this stuff with you. I'm using Visual Studio for Mac, but it doesn't matter what you use, whether you use a Mono Develop or Visual Studio Code or anything else you like. So what I want to do is I want to do some of this with you again. So this is what it looks like. So you can refer to the finished code online. That's why I gave it to you, right? But I want to kind of do some of this again. And I want to kind of relate this to the equations we're using and how I came to all this. So just to start this off again, and I want to talk about this. The one thing I won't change is my time. My time is plus equal to fixed delta time. We'll talk about that. But the rest, I'm just going to get rid of eventually, okay? So in order for me to do this nicely, I'm going to make a new scene so I don't kill this scene, okay? The only thing I'll be fooling around with is the script. So I'm going to go into scenes. I'm going to take scene 2, and I'm going to duplicate it, right? So again, to duplicate the scene, it's Command a D on the Mac, or I think it's Control D on a PC, right? There we are. And it's called nicely scene 3. That's good, right? So here's scene 3. Now, what I don't want in scene 3, I want to start off with some basic stuff, and we're going to talk about the 3 different types of motion, right, that we're describing here in physics. So one of the things we said was, this is the first type. The first type is where I drop a ball down, all right? And we kind of did this in class, right? And I have some equations here, right? And let's go through. The reason why I copied everything is because I want to get rid of all this for a second. So all this stuff here.
That's the that's
just a script.
Copied through both scenes.
Yeah, that's fine. I'm just doing it. You can make a new script if you want. Okay. But I also got the finalized script online, so you can always look and see what I did there. I might do something different today, but at the end of the day, it's very similar to what we did. So in our fixed update, one thing to know in any kind of game is you have a game loop, of course, right? You guys should all know that by now. And the different looping structures we have here in Unity, I'm just going to get rid of all this stuff so we can start over, right? And I'll talk about this a little bit. So none of this. And again, I'm doing this because I want to start from scratch so you guys can see some of this again. All right, so I've got my ball and I've got my fixed update. But one thing I want to do is set up this, and I want to make it public so we can see the time. My time, which is, of course, of type float, right? So float, we'll call it time. And all I wanted to do is I wanted to count a number of frames. Okay, so why am I having a problem here? Oh, I'm missing a closing brace. Here we go. Right, so that's what I want. I want time to count each frame. Right now, remember that when we work with our code, and guys and girls, you need to kind of understand this stuff, right? We cannot just apply basic physics formulas, right? We have to sit there and go, okay, I'm working in frames. Physics normally works in seconds, right? I have a number of frames I'm going to go with, right? And what I want to do is I want to kind of come up with how many seconds, how many frames per second, right, I'm working with, right? And it's not the frames per second, the frame rate, never mind, by the way, I'm not talking about the frame rate. I'm talking about how many frames I'm going to count as a second, okay? So normally we count seconds, and for every second or every portion of a second, right, we're going to have this frame rate, all right? That's going to happen. So example, if I capture something, let me just use a little drawing program that I like to use. Let's just use, let's go use Sketchers Pro for a second. There we go. And so this is going to, think about this as my whiteboard equivalent. So I just want to put these little things here. So imagine if I've got, these frames. So I've got like one frame and then there's the other one. And every time I move my mouse, there's another frame. Sorry for this, but I can't see what I'm doing. So here's the other one. So I've got all these frames. And in between frames, I have a ball moving. So it starts off over here, and then it's going to go over here. And then the next frame is maybe a little longer. I don't know why, but. And then do you notice these are the motion of the ball as it moves from one frame to the other. That's what's happening, right? So it's going to go from this frame, to that frame, and I'm drawing blind. So yeah, there we go. And I'm talking at the same time. It's lovely times, right? But you can see what happens. There's each frame, the ball moves a certain distance, right? Well, this is like it is in seconds. So for example, if this was seconds, this is 1 second, and this is like 2 seconds, and then we got 3 seconds over here. Maybe this will be 4 seconds, right? But we don't have seconds. We have frames in when we make games, right? How many frames, how many times the screen gets refreshed? The screen is continually going to be refreshed every frame, right? So we kind of need to create this idea of how many frames are we going to use per second for our simulation, okay? So if I go back up here, I want to create this, we'll make it private so we don't get messed up with. We'll make it private, and we'll just call it It's going to be of type float, and we'll call it FPS. Please don't look at this as frame rate. Okay, it's not the frame rate of the game. It's how many frames per second. How many frames am I going to count for each second of real time? Okay, so that's the second measure. The other thing we have to think about is when we make a we do some physics calculations in real life. What we have instead of this, right? And let's see if I can actually erase this. Yay, I even have an eraser on this thing. All right, let's just go to over here and grab this big eraser right here, and let's just erase. There we go. That up there. That's much smaller than I wanted. Let's move this. Let's move this big. No, that's not going to do it. And that was actually better off just doing this. There we go. So I'm just going to do Control New. How about that? No. Don't save. All right. So so when we start talking about this, think about, you know, if I have a tower, some kind of tower or a ledge, right? So I have this tower, right? And I want to do this simulation where here's the ground, right? And you have a certain distance. And this typically is some kind of distance in meters, like, for example, 50 meters, right? So I've got 50 meters here. But that's nice and all that we have 50 meters. But what I really want to do is, this can't be 50 meters, right? In some kind of game simulation, a 2D game simulation, maybe this is going to be some kind of pixels, maybe something in pixels, right? You know, so we can't just say 50 meters, right? There is no meters in the game. So we have to figure out, like I said before, how many, you know, pixels per meter. We got to figure out this rate. So we're kind of scaling our game too. How many pixels per meter? Now, this is the challenge for Unity. Unity is written in meters, but actually it's Unity units. We have to think about, right? Not Unity meters. So we go back here. I'm going to create this same thing. I'm going to call it units per meter, not pixels per meter, because we don't have any pixels here. And we're not doing a pixel perfect game. So it's going to be units per meter, right? And units per meter is going to be basically a ratio of how many meters. If I say a meter in some kind of problem, it's going to mean X number of units, whatever that unit number is. Okay. What do I mean by that? Well, if you look at Unity, right, you have a scene. Here's your typical scene. And if you look at the ball in this particular case, so I'm just going to click on the ball, right? Notice that the position on the transform is -17 and 4 and 0, right? Well, 0, 0 is actually the middle of this camera right here, right? Now, there's some tricks I can do with the camera to zero it out. Right now, what I've done is I've made the camera orthographic. I know it's hard to see, and I've made it the size 15, right? That's what I've done. I also can look at the near and far plane, but I don't care about those things right now. In fact, the far plane, 1,000 for a 2D camera, way out of whack. I can probably take this right down if I want to like 100 or less, even 10, right? Because I'm still going to see everything, right? And this is the far clipping plane, the far plane and the near plane, okay? That my camera cuts off. And if I actually put this into 3D view, you can see that now it's a box, okay? So a shorter box than it was when it was 1,000, okay? So this presents some issues. The other problem I have is when it comes to lighting and everything else and blah, blah, I don't care about any of that stuff. But what we have is our camera has a viewport rect. And notice that the viewport rect here is the 0, 0 point, where the 0, 0 point is, right? And my width and height. Width and height. So notice that my width and height is 1 viewport wide by 1 viewport high. So if I turn this to 0.5 as an example, then now we only have half a height, right? So then my game would kind of look like crunched like this, right? So it would only be half high, right? And if I did the other way around, if I change this back and I change the viewport to 0.5, you can see that now you can't even see the tower anymore because you only see part of the ground, right? Because again, I'm only using 1/2 of the viewport, right? The width of the viewport. And this is what this does. It gives us kind of a height and width, right, as an example. But what it doesn't do, it doesn't allow us to move our coordinate system too much, right? So our coordinate system starts in the middle. Unless I choose to go full on 2D, right? it doesn't allow me to do pixel perfect units, and I wouldn't want to in Unity anyway, right? Just putting it out there. So because of this problem that we're engaging in, right? Our size of the camera, which is 15, what does this mean, 15? Well, let's take a look. And again, I'm just specifying so we understand how this works together. And you notice that if I go all the way to the top, right? All the way to the top part of my units here, I get about 15.93, and I go all the way to the bottom with my ball, right? And you can see that again, I get around -13. If I kind of come out of the screen, it's about almost -15. Top of the screen with my ball is, again, -16.59. It's not really even, right? The way it's been done, right? So there's a bit of an issue. So the ball is going to be some kind of units away. And if I want to know how big the tower is in units, right, you can see that the size of the tower is approximately or exactly 16.46 units. Most of the time, this means meters in Unity, okay? So let's just make it even. So we'll say 16, right? And we'll bring the tower down. Now, this is not including, 16 is not including the base of the ground, right? Because the ground also adds height. The ground's height right now from a scale is 1, right? And it's also 39 wide. Let's make it exactly 39 just to make it so that it's not completely whacked. So 1, just to give you a scale as an example, 1 plus 16 is a total of height of around 17 units. 17 units. Let me just zoom in there so you can see what I'm talking about a little bit more. Right, so this is what it looks like right now. Okay. And what I want to do is I want to simulate this ball dropping down like I did earlier, right? So what I want to do is every tick of the clock, every tick if I was to move it down per frame, every frame, right? That means every time that the time ticks, it'd be way too fast. Like for example, if I said the vertical distance or the acceleration or whatever I want is going to be every frame, I'm going to change the y value by a number of units. It's just going to fly, right? Even if I put 5. So for example, the vertical speed. And so therefore, we need some kind of conversion, some way of cutting things down so it's more realistic in terms of our little simulation. Notice also that I'm using fixed update, which gives us a steady beat of the clock compared to update in Unity, as well as fixed delta time, which gives us, again, a pretty steady beat. And if I was to just try this out the way it is, if I was to go to debug.log, and if I put in the time value, just to show you this, what we did last time, you can see that this time value is going to be not just seconds now, it's going to be every 0.2 seconds. It's going to accumulate in terms of total time. So if I was to run this thing, without any kind of errors, you can see that the console, as I go down to the bottom, it's going to continue to accumulate 5.6, 6.7. So some portions of time, okay, which is kind of cool because if you notice, it keeps growing slowly, 1 second at a time, but we get all the intervening parts of the second, which is good, right? Because in real life, it may not take us exactly 1 second to go from point A to point B. It might take us 1.2 seconds, right? So we have that granularity here, all right? But we don't want to travel if we don't want to make it 1 second per frame, that's crazy, right? We want to kind of figure out how many times it takes. How many frames does it take right now? How many frames do you think it takes right now to form out a second? Seconds per frame.
30, 50.
Well, no, let's just check it out. If I run this really quickly, if I said run it and then stop it, so I stop it right away, you can see that the console, right, it gave us a portion like 0.02, right, 0.04. Each beat is 0.02 seconds, if you will, right, 0.02 seconds, which is about right? It's about 0.16 milliseconds or 16 milliseconds for every frame. So it's not exactly 60 frames per second that we're getting. We're getting actually less here, okay? Because 60 frames per second is 16.666 milliseconds, something like that. So we're getting slightly less. All right, so you can see it takes quite a number of frames to get us up to a second, right? And we want to figure out how long it takes, right? Without any kind of crazy calculation, if every frame is 0.02, right? 0.02, how many of those divisions that I need. So if I calculate this, if I said, well, it's about, you know, I have a full second, so that would be 100, right? And if I take 100 and divide it by, well, if I'm adding 0.02, 0.02 is 2% every single time, 2%, 2%, 2%. How many times can I multiply or add 2% until I get 100? 2, 2, 2, 2, 2. I keep adding twos, right? Well, 50, right? 50 times. So pretty much our seconds per frame, if you will, or frames per second that we're getting is around 50, not 60, okay? With this measurement system that we're using right here, 50. So that means that I want to divide, for now, what I want to do is I want to start off with a frames per second rate as a scale, right? I'm going to say that this.fps, right, is equal to around 50, okay? I'm going to start. Units per meter, I have 16 and 1 units. Are they going to be, each of them is going to be a meter? Then it would be 1 for 1 right now, right? If I said if each unit was a meter, right, then it's a 1 for 1 ratio. I don't have to divide by anything. But what about if I said every unit is 2 meters, right? That means it's like 32 meters up instead of 16 meters up, just a different scale, right? So it really depends on the scale. For now, let's just use 1 for 1. So for now, I'm going to start off with a units per meter of 2, okay? So 2 units per meter. And we're just going to put in, just so that we satisfy the floating gods, right? Floating point gods. Okay, so once we have frames per second and units per meter and we have our time scale, now we can start applying our calculations. Now what I want to do is I want to drop the ball. So the initial velocity, I'm going to have some kind of initial velocity on the x-axis and some initial velocity on the y-axis. But I want these values to be calculated, right? So we're going to kind of come up with a couple of additional private parameters. So private for now. And we're going to call them velocity y. There's my velocity y, right? And I'm also going to have a velocity x. Okay, so I've got a velocity y and a velocity x. This is all set up for me, right? So velocity at y, everything we're moving on the y velocity, on the y coordinate space, okay? Up and down, right? Now remember, as I'm moving down, it's becoming more negative. And as I'm moving up, it's becoming more positive. So if I move down, if I add, right, velocity, that means I'm going up, right, in our time scale, right? If I subtract velocity somehow, I'm moving down, right? And when I say velocity on the x and velocity on the y, this is the two components that we're dealing with right now. Normally, we'd also have acceleration across different axes. But for now, we're just going to use a floating point of acceleration. We're going to say acceleration only on the y, okay? Just so we really be explicit. Acceleration on the y-axis, right? Because we don't have any acceleration on the x-axis. In order for us to have acceleration on the x-axis, we have to have a force, like a rocket, that's pushing us to accelerate you know, along the x-axis, along the horizontal, okay? We don't have that in these equations. This is just like a ball falling or something, right? Inside of our start method, what we want to do, right, and sometimes some people also call it the start function, what we want to do here is we want to initialize as much as we can, right? So we know that I want to set up our initial state. So our initial velocity, I'm using this keyword to be explicit, on the y-axis, right, is going to be 0. So we're going to say, hey, there's no velocity on the y-axis. I'm not actually pitching the ball down or throwing the ball up. I'm just dropping the ball, okay? And also, at the same time, for this first example, our velocity on the x-axis is also going to initially start at 0. Right? So we need those. We know those two things are starting. We also know that we're always being brought down by the acceleration. So we're going to say that this dot acceleration, right, along the y-axis is also equal to a negative 9.8 something. But hold on a second. Why is this really valid? If I said 9.8, because remember, we're talking about our units per meter is 2. So what should I really do to my acceleration, right? In fact, what should I really do to my velocity x and velocity y? What should I do? Because remember, we're moving in meters per second in the real world. So what should I do here? we're going to move units per meter, right? How many units per meter we're moving, which means I got to divide that, both parts, both velocity and this. And we're going to do this automatically here. We're just going to say, we're going to set the values right here. And just for now, they're 0, right? But I want to divide this just to start off by units per meter. So units by, something by 2, 0 over 2 is still 0. So it's not going to really matter. But I want to do the same thing for, my acceleration. So why am I doing this? Because I'm scaling my acceleration and my velocity by my scale, whatever the scale is. If I dropped units per meter to 1, there'd be no scaling, right? I'm making it 2, so that I'm saying that the actual the height of my tower is twice as high, right? Because each unit is actually 2 units. Okay, that's what I'm saying here in this particular case. So we got acceleration, we got velocity. We also need position. Okay, so position across the x-axis. That's the final position. And if you notice, we have in our PowerPoint presentation, we have this. We have our position on the y-axis and our position on the x-axis. That's what these two first equations do. They calculate the position of our object along both axes, right? That's what it does. So it's a position function is what we have, right? Those are position functions. So because they're functions, why not make it that? And that's what I didn't do last time, because I wanted to kind of do a quick demo, which turned out to be a disaster. Train wreck, right? Is what I used to call it, right? But let's do that. So we want to kind of make this. I want to find the distance on the y, right? I want to calculate the distance on the y and the distance on the x, right? That's what I want to do. And I want to make that their own function. So I'll say void, we'll say distance on the y, right? To calculate our distance on the y. And we'll also say void to calculate our distance on the x. Okay, so we've got both those two functions happening. Distance on the y, distance on the x. Right now, we want to calculate the distance on the y, and we need to use a couple things to calculate that. We need to use time to calculate distance on the y, up and down. We need to use acceleration. We need to use velocity. Okay, all those things play a part. And if you look at the initial equations, going back to this, velocity times time. If velocity is 0 right now, that's going to be 0, right? We also have half AT squared, time squared as well. And that's going to give us, we're going to return some kind of distance or position on the y, right? That's what it's going to do. Now, instead of returning something, I'm just going to set the distance here every frame. I'm going to set every single time it's going to pass. I'm going to call, instead of my debug, I'm going to call both the distance on the y and distance on the x function down here. So I'm going to say distance, calculate distance on the y, right? Oops. And calculate the distance on the x. I want to find those two values. That's what I'm doing, right? And I'm doing that every frame. Every fixed update, I'm calculating both the distances of the ball, right? So inside of my distance y and distance x calculations, this is where everything, this is all the magic, where all the magic happens in here. I'm not returning anything. I'm just modifying the transformed position, right? To whatever the new distance, the new position is going to be. I'm calling it distance, but you can also call it position. The new position x and position y. And if you're really a critic, you can always just refactor rename like this, right? So refactor rename, and if you like to call it position on the y, I'm okay with that. Or because I'm going to talk about it from a programming perspective and norms, right? And then position on the x. You can call it both ways. It doesn't really matter to me. Oh, that didn't work. Position on the x. So either way, whether you want to talk about position or the distance from the origin, it doesn't matter to me. Okay. Let's use position to make it more clear. Okay. So if I'm calculating position, it's going to be a function of the first one for dy, vt plus 1/2 at squared. So how do we do that? So we're going to say that, well, we want our new position. So we're going to make a variable called new position, right? And my new position variable, notice in C# you can do var, because var just means, hey, implicitly tell me what my variable is. It's not loosely typed. Once you decide what it is, it stays that way forever in C#, right? But I want to calculate my new position. And what I want to say is vt. So, and this is on the y only. So velocity on the y, right? multiply by the time function, whatever the time is, right? And that's the first term, right? This part here is the first term. So velocity times time, okay? Plus 0.5, we'll put this inside of another little bracket like this, so that we're not confused, 0.5 times at squared, which is acceleration. Bring that in bracket. Actually, I can leave that like this. Fine, that's fine. Just making it so the brackets just help you see that what they all are, the terms, right? Now t squared. I could use a math function. I could use math f dot power, right? But we only have, it's only going to go to the 2, right? It's only a square. I mean, I could use math, if I could spell dot power. I could use the power function and go from whatever the time is. This is one thing I could do. So for example, the first one is time, and then to the power of 2. That's the equivalent to multiplying it by 2 or by itself. That's a new position. So this is equivalent to writing this, Vt plus 1/2 at squared, right? And that calculates the new position. But we want to take that new position, which actually is a scalar, which is double, right? And the reason, by the way, why I calculated it as a double and not as a float, right, is for 2 reasons. It's trying to figure out what it was. And because I had 0.5 instead of 0.5f, 0.5 is more of a double value than a float value. So C# figures that out as a float. I want it to be I figured out a double. It's supposed to be a float. That's what it is. I want to take this floating point number and I want to modify my y position, right? My transform. Now, there's a bunch of ways to do this, guys, so please bear with me while I do this. So it's transform dot position, right, is equal to a new vector 3 objects, because we're in 3D. We can also use a 2D object, doesn't matter. And I want to take whatever my position is right now, so transform dot position, right, dot x. I want to keep that, and I want to change my y to the new position, right? But hold on a second, you're going to say, shouldn't it be based on the initial position? And the answer is yes, it should. So I'm going to take my transform dot position dot y and then add my new position to it. And just I'm going to break this up over a couple lines so you can see it. That's just the only reason why I'm doing it, so you can see this. And then, of course, we don't want the z component to change at all, so we're going to just change that to 0f. Okay, so that's what the first part is. So the new vector that I'm making is, I'm creating a new vector, I'm assigning it to the position, right? And I'm taking the old position values, x and y. I'm only changing the y value to add the position. I could do position y and position x together, but I want to separate the values so you can see how I'm breaking up the components of the function, okay? All right, cool. So this is this part. On the x-axis, right, notice that first, by the way, we should get velocity, because the initial velocity was 0, and time, doesn't matter what the time value is. We're going to get 0 plus some value. Okay, that's what's going to be here. Here, in this case, right, we're just going to calculate the same thing. We're going to say new position, right? Now, this is new position on the x-axis this time, is equal to velocity on the x-axis times time. And if you look at that, that's what it's doing. Velocity on the x-axis times time. All right, so we're going to say velocity x, right, times time. And that's what the answer is for our new position. And just to keep the same, so it looks very similar, not because I need to in any way, I'm just going to put it in brackets. I don't need to, but I'm just putting it so you can see that this is one term. All right, and then similarly, I'll do the transform. So I'll do transform dot position, right, is equal to a new vector 3 object. I'm using a vector 3 for another reason. By the way, I want to stabilize my z coordinate so it doesn't go all over the place if it hits something, right? And just bringing it down here, I'm just going to bring it down to the next line. So I'm going to say transform dot position dot x plus my new position. It's kind of the opposite. And then plus my transform dot position dot y, and then 0f for the z coordinate. You guys see all that? And again, this is all untested. I haven't tested the code. I don't know if it's going to do anything. I don't know if it's going to mess up like last time. I don't know, right? But let's see what happens. Does this make more sense to you than what I did on Tuesday? So it's kind of more organized. I've broken it out to two functions, and that's what we're doing. We have two functions to decide the acceleration, the motion, the position of both the y and the x axis. And I'm doing that every frame. So every frame I'm changing the x, and then I'm changing the y. And then changing the x, and then I'm changing the y. Every frame. It's going to keep hitting that every single time. So we should have a smooth motion. Now, if it's too fast, right, we can cut one of the two values down if it's too fast for us to see the motion. All right, let's go forward here and see what we can do. So we're going to go back to our Unity now. This is a great place to test. We're going to stop running this thing. And now we should see some kind of motion where I'm dropping a certain amount of time. I'm taking the ball, it's starting off here, and wherever the ball is, it's just going to drop. So let's see if this works somewhat smoothly. Maybe not. Yeah, right, and it accelerated, right? So it kind of went down, and you saw it kind of went down. Now, if that's too fast for you, and you know what, to me, that was a little fast, right? What can I tweak? I can tweak one of the two things. I can take the time down, so I can say the time between ticks of the clock, I'm going to expand a little bit. Right now, it's 2, it's 50. I can change the clock. So every 50 frames is 1 second right now, okay? Or I can change the scale. I can say it's a much taller tower than it was, right? Which means my scale is going to be dropped. My velocity is going to be slower, right? And my acceleration due to gravity is also going to be slower. So let's do that. Let's say that instead of our ratio, notice our time is here, right? But I'm only allowing us to see that. But then what I want to do is change my ratio here. So in the top, we're going to kind of put these as public values in a bit. But in the top where I say 2, I'm just going to move this to a value of 4. So it's going to be half as slow, right? It should be half as fast. Let's take a look. We're just changing the UPM from 2 to 4. And if I run it again, you can see that I do have accelerated motion, right? But it's not as fast. Okay. I need to get it to stop. I don't have any colliders, and I'm not talking about collisions today, right? I'm only talking about motion. And what I want it to do is stop at a certain point in time. Now, we're going to have a bit of a problem, like we talked about, right? And why may not this work properly? Because if I want it to stop dead, right, on a particular point in time, right, the only way I can do it is, well, if it reaches this point, whatever that point is, right, the point of the ground as an example, stop. We don't want it to go below a certain y value, okay, ever. Okay, so, but I want it to kind of, almost like a dead reckoning. I want it to be exactly where it's going to be. And that's kind of tough. Why is it tough? Why would you say that's tough to do? To position it exactly at the ground every single time? Anybody have any idea? No? All right, well, let's take a look at this in terms of frames. Okay, so if we think about this, if I draw this out again, right, and if I go to the top, right, so let's say the ball starts off, around right here. So here's the ball. And this is the top of the frame. So it goes here, and then it goes here, every frame, right? And it's going to accelerate because it's going to continue to go faster and faster. It's going to go here, right? And then it's going to accelerate to here, right? And then it's going to accelerate to here. If this is the ground, right? Maybe it's going to pass the ground here at this point. Let me just undo that one. Maybe at this point, it's going to accelerate so much that that's in the ground the next frame down here. Right? You see that because it's accelerating, and all I'm doing is 1 frame at a time, right? So even if I wanted to, and if I stopped it, if I said, stop it exactly where it's going to be, you know what it would do, right? As it approached this part right here, it would stop at some point as close to the ground as it could. And it could be different every time depending on my function, my update function, how good it works, right? So I need to bring it back up to that level, okay? I'm not using colliders at this point, remember? Just simply moving it in terms of motion. And this is part of my exercise, right? So I'm going to go back to my to Unity and kind of take a look at the ball where it's positioned. So the original position on the y-axis is 4.478, whatever it is. But I want it to stop somewhere when it gets down to about right there. And if I want to frame select that, you can see that that's probably about right? Maybe a little bit lower. There's the ball. And you can see it's going to be negative 12. And if I said just negative 12 by itself, negative 12.2, negative 12.2. Right, some value. But negative 12.2 is where our ground is right now. That's where it's going to sit. And we're just going to undo that change. Negative 12.2. But I want it to be, for now, I want it to be in my code. And later on, we'll bring it out of my code into the inspector, right? So we're going to kind of create another value. So we're going to say our private float. We're going to call it the ground, right? And we're going to use the ground. We're going to set the ground here, right? In Unity units, we're going to say that this dot ground is equal to 12.2. Okay, so some kind of value, and it's going to be negative 12.2, by the way, because it's a negative value below. It's below the middle point of the screen, just in our simulation. These are all things that you can set up for your world. Your world, if you're making a platformer, that'd be the same for you. You'd have to set up where the ground is. You'd set up all this stuff. This is from scratch, by the way. No colliders, no collisions, right? And I want to check. I want to say, well, here's my position, right? And my position is going to be checked. But I don't care about my Y position or my X position being checked anymore if I've reached the ground. Okay, so if my ground, if I've reached it, if I'm greater than or equal to the ground, I want to stop, right? So that's the only time I want to check this is if my horizontal position, my position dot Y, is greater than the ground. Okay. So I'll say that. I'll say, well, if my transform for the ball, right? My transform dot position dot Y, right, is greater than the ground. Has to be greater than. Can't be greater than or equal to. If this is true, then calculate all this stuff. Right, so that's what I wanted to do here. I want to say do this only if my transform position dot Y is greater than the ground, right? Otherwise, if it's at the ground, I don't want it to keep going because we'll lose our ball, right? And what about if it's not greater than the ground? What if it's less than the ground? What do we do then, right? That means it's falling through it's going to fall through the ground. It's already fallen through for some reason, which we need an else for that because it might do that. Else, right? We're going to say that our transform dot position is equal to the ground, right? Where it's going to be a new vector3 object, and we're going to say that our the lower part of our transform dot Y is equal to the ground, right? But our X, sorry, that's the X, is going to be equal to the transform dot position, sorry, dot X, and then our Y is going to be the ground because it's going to stay at the ground, and then our Z is going to be F again, 0, right? All I'm doing is saying, well, if it goes past the ground, put it back up to the ground, right? Now this is going to happen every frame, right? So we should have some weird flickering effect, right? Because it's going to kind of come up, come up, come up, come up, come up, right? Or it's going to check to see that this is true, so it's just going to set it every time, right? Let's see what happens. So I'm going to come back to this, and let's just run our little app, see how it works, and boom. And that's what I wanted to get when we were together on Tuesday, right? And if I run it again, if I rerun this thing, right, then you're going to get the same motion. And the great thing about this is this. Now, what if, here's a crazy thing, my timer is still running, right? My timer is still running. If I was to pick this up, would it just drop back the way it should be? In our simulation, no, it will not. It will accelerate even faster because take a look. If I keep trying really, really hard, it's going to really be super fast because look at our time. Our time is like still probably going, right? Our time is going to go on forever. It's never going to stop. So we can't let that happen. We got to also say, well, when the ball hits the ground, timer stops. We don't want to actually accelerate anything. We don't want to keep moving everything when the timer stopped, right? And that's what's happened here, right? We put the time inside of the ground calculation, so we stop the time, right? But when it hits the ground like this, we want our time value, this time value, right, to be initialized to 0 as well. 0F. You see that? Because when it hits the ground, my time now is 0, right? Because when I raise it again, it's like I'm starting from scratch again. I'm raising it above the ground and starting from scratch. Now I'm doing the countdown again. Because if I keep what the old value is, it's going to really accelerate quickly, right? Which is bad. So I've got to reset my time value. So let's go back to this. So down to this, run it. Should still run the same way. Bam, right? But if I go back to my scene somehow and I, in runtime, I pick up my ball and carry it up, then it'll still drop down like as if it's got like I'm starting the timer from scratch again, right? And you can see that the time keeps starting over and over again. I'm kind of creating my own physics, and that's what I wanted to accomplish Tuesday, right? With bad results, okay? But let's suppose, and this is what happens when you live code sometimes, it is what it is, okay? So we've handled the first type of equation, this one, right? Where we just dropped the ball. There is no any kind of horizontal impetus. I haven't actually given it any motion across the horizontal at all. And my vertical is also negative, right? I haven't thrown it up into the air, right? I haven't thrown it into the air. I'm just dropping the ball. That's all I'm doing right now, okay? What happens if, and we're going to test these values, right? What happens if I want to do the second part of this equation where I have a little bit of force applied on the x-axis, some kind of velocity across the x-axis every frame? So what I mean by that is, let's suppose if I go back to my diagram here, right? And let's just draw this again. It's just easier. So I have my diagram, and here's the tower. So I've got my tower, right? So up on the top, my tower way up here, and there's my really nice straight line. You like my straight line? Awesome. And here's the thing. And what I want is the ball is way up at the top here, right? It's going to start dropping down. But not only does it have some kind of gravity pulling us down, which is G, right? But we also have some kind of, a velocity across the x-axis this time, right? We don't have any acceleration across the y-axis, but we're going to give some kind of value across the x-axis initially, almost like a muzzle velocity. I have a cannon, it's sitting on top of a tower, and I'm firing the ball straight, right? That's what I'm kind of doing. Or I'm tossing the ball. I'm almost like bowling off a cliff. I'm doing one of those. Whoa, bowling off a cliff. And if I do that, if I give some kind of velocity across the x-axis, then going back to our code, right, what we can do is we can change some of these values. We can say, well, we got a pretty good thing, but our velocity across the x-axis isn't 0. Let's give it some small value like 2. So 2 meters per second, or 2 units per meter, however you want to talk about it, divided by some value, dividing it by our world frame. What I've really done with UPM and FPS, those two values, units per meter and frames per second, how many frames it takes to accumulate 1 second, right, is I've created my frame of reference. And it talks about frame of reference in the next group of slides. I have a frame of reference. I'm the observer. And my frame of reference in this world, I'm creating my frame of reference for the world so that it simulates physics, okay? So I've got this 2 units per meter, 2 divided by units per meter that I'm moving at. So I am moving at some velocity x. Let's see if that's too fast or too slow. So I'm going to go back to Unity. And I'm going to run it again and see what happens now. So when I have this value of 2 units per meter, I get some kind of value like that. You see that the actual, I get a bit of a curve, right? It's not straight down. I get a bit, it kind of has this effect of where I have some velocity across the x and some velocity pulling us down across the y. The acceleration on the y-axis is due to gravity. Okay, so that's really how it looks right now. Almost there, we're almost there, right? Now let's add a little bit of acceleration on the y-axis. But I want to add acceleration on the y-axis downwards. So I want to pitch it down. So I'm actually not, instead of throwing the ball, instead of dropping the ball or bowling this way, I'm actually kind of throwing it down at an angle, right? Some kind of angle. And it's going to be an angle that we can't calculate right now, right? But I could do that too. I could have this function where I'm going to kind of throw it down at, downwards and across at the same time. That's kind of a weird motion because normally we don't do that kind of thing. We have a cannon or something like that. But if you can imagine that I have 2 forces, one that's acting downward upon the ball and another one that's acting across the ball, right? So the velocity in this particular case on the y-axis, I want to put to negative, we'll give it an extra impetus of -1, right? F. And just to make it fair, we'll make this F as well. Everything is F. Well, this makes it move even faster, and it's hard to see the difference, but you can see that on the y-axis now, it's actually faster falling down because we have additional force going down, okay, on the y-axis. If I turn that force upward, and I say, let's say, for example, I said it's 5 meters, per second going up. So to kind of simulate that, right? So somehow I toss it up and over, like something like this, up and over, right? At some angle. I don't know what the angle is right now. I just know the velocities. If that's the case, then I would actually change this value. Let's say make it 5, a positive value. And if I check this out again, we should see a different kind of motion, right? Where it kind of tosses up and down. Does that make sense? So all these kind of things, these are things we can simulate by creating we're using the 2 first equations. That's what we're doing here. Are we clear about the first 2 equations, how they work, right? You're going to get problems, and we're going to look at some of those problems later today, right? Where you're going to get a problem statement, and you're going to have to try and plug in the values. Which equation is the right one to use? All right, so that's the first situation. Let's look at the second situation. The second type, and we just did this, right? The second type of situation, and we did break it down in horizontal and vertical. The second type of projectile motion is we're actually sitting on the ground, okay? We're actually sitting on the ground plane. And I have a kicking angle instead. I have almost like an angle of attack. Think of it this way. I have a cannon that's on the ground, and I'm pulling up at some angle, theta, right? And I want this thing to go up and then hit the ground. Okay, but here's my problem. Remember I had that ground check? I have the ground check. This is if it's at the ground, then we're actually gonna, not go anywhere for now. For now, I'm not gonna put it quite at the ground. I'm gonna put it a little bit above the ground, so it's not quite at the ground level, right? So that way we can actually work. Otherwise, if it's just at the ground, it's gonna stop. It's not gonna do anything, right? Because that's our way we work, okay? Without anything else. Now notice that we also have another variable. We have theta, which is our angle, right? So let's put that into play right now. So I want to kind of put it back, and I can see that I have this stuff here. I'm going to add angle, right? And I want you to think about this again as, just want to put it down here, as angle of attack, right? And it's going to be a floating point number. Here's the thing when it comes to angles and computers, right? They all need radians, right? Which is kind of sucky. Luckily, Unity has a rad to radians to degrees, rad to deg method that we can multiply by our angle to get our radians, right? Or deg to rad. It actually should be deg to rad, not rad to deg, right? There we go. So we have our angle, and let's set our angle here, the initial angle, to 0. So we're going to say that this angle is equal to 0, right? And then we're going to multiply the angle by some math f times. And again, I want you to think about this as degrees to radians, right? Which converts our angle to radians, okay? Because we're going to need radians with whatever we do, okay? Okay, cool. So we have our angle. That's one of the things we've talked about, our angle of attack, right? And typically we also have something called a velocity, a final velocity. It's not a velocity across the x-axis or a velocity across the y-axis. It's our final velocity, our velocity, that we give it almost like a muzzle velocity. I have a cannon. This is the other way around, okay? I have a cannon that I'm applying some kind of muzzle velocity to, or a gun that I'm firing in the air, right? And the muzzle velocity is the velocity of the bullet or the projectile that leaves the muzzle, the speed that it leaves the muzzle. How fast is it, right? And it's usually described as a vector. Okay, so if I was going to draw this out, just to give you this exact kind of diagram, again, I'll make a new diagram. Oops. I meant to do that. Think about the ground plane. So I've got some kind of ground plane here, like this. So I've got the ground plane. Right, and I've got on the ground, near the ground plane, I have some kind of cannon or something like that. Let's call it a cannon, right? And what I'm going to do is I'm going to fire a projectile straight into the air, and it's going to have some kind of it's going to be, the velocity is going to be expressed in terms of a vector, some kind of magnitude and direction. Okay, that's what a vector is. That's the velocity. But we also know that this thing, this second situation, so it also has an angle that goes the angle of attack, which is this angle right here, right? This is theta, right? So this is the kicking off a ball, we're kicking it, or we're launching it with some kind of projectile weapon, a cannon or a gun or something like that. That's what we're doing. Okay, different situation, different equations that are required. All right, so we have our ground, we have our angle, whatever that angle is. Right now it's 0, right? So it's a 0 angle, right? And we need an initial velocity. So almost like a velocity by itself, not a velocity x or a velocity y, but rather a velocity. We're going to kind of put it in terms of the same things. We're going to say this dot velocity. How about I make a velocity first? So I'll make call it like a kicking velocity or a final velocity. We can just call it velocity with a capital V, right? So the velocity will be some amount of velocity, right? And then divided by UPM. Again, we're scaling it according to our world scale. Our world scale, depending on how it is, we're dividing it by UPM because it's some kind of units per meter, right? We don't know what the scale is. If I kept it at 1 for 1, it'd be really super fast, like crazy fast, right? It wouldn't be usable in our game. Okay? Okay, Corey? And the reason why this is like this is if we really did it 1-to-1 scale, then on their screen, we have a screen that's actually a meter. We'd have to have a meter on our screen to do 1-to-1, right? That's what how we have. We don't have a meter. We have some kind of portion of something that looks like a meter, but we don't have a meter. So we have to create our own scale, right? All right, so we need our velocity. Right now it's 0. And some of this stuff, our velocity on the x-axis, on the velocity on the y-axis, we might be able to keep some of this stuff. Acceleration is going to keep, the ground is going to keep, the angle right now is 0 for now. We're just initializing. And what do our equations tell us to do? So we've got this kicking angle. And if you notice that I'm going to use for each component, the velocity across the x-axis and the velocity across the y-axis is going to be some v cos theta for the x and v sine theta for the y. We talked about this way back. What if I use v cos theta and v sine theta now for what I have already? I already have an equation, right? What if I subbed in, for my first two equations, the first situation that's way up here, right? Here's my first situation. What if I subbed in, instead of vt and vxt, what if I said v cos theta t and v sine theta t? Would that affect anything if my angle was 0? No, right? Because what's sine of 0? 0, right? Or sine of 0 is actually 1. I'm not wrong. 0, no. Cos of 0 is 1, right? So I get nothing there on the x-axis. Sine of 0 is 0, so you wouldn't get any kind of angle. So there's no lift angle from one or the other. So when I multiply by cos theta or sine theta, I'm not getting anything. So I can simply just do that now. I can kind of go in here when I calculate my velocity. I divide it by UPM, right? And I can multiply it by my angle. So if I want to find and I'm not talking about the velocity strictly on the y, but I want to find the y component of my velocity, right? And I'm only going to do this once. So just to make this happen, I'm going to pull this angle stuff up a little bit higher. I'm going to put it just underneath my UPM, right? Here's my UPM. And I could multiply by my velocity. So my velocity y then could be my total velocity. This is the second part, the second thing. I'm just fooling around with the equation so you can see this. Could be this velocity, right? So instead of having some value here, like 5f times UPM, imagine if I didn't have these values. I don't know how fast. I don't know what the y component is. I just know the angle, right? I want to find the y component from the angle. That's what I want to do, whatever that y component is, right? And that's going to be my standing velocity every frame, right? Because I have an angle and I have some kind of velocity on the y and some kind of velocity on the x, right? X, y. All right, how does this work? So I'm going to say something like this. I'm going to say, well, my velocity then, forget about divided by UPM, my velocity then, take my velocity capital V, is the second type of equation, right? I'm going to multiply it by math f for the y component sine theta, right? I'm going to pass in my angle, whatever that angle is. And the same thing goes for my velocity on the x. I'm going to say my velocity, right, times math f times cos, and then put the angle in there. And what I want to do, this is the velocity on the x and the y, the initial velocity on the x and the y. That's what's happening here. And I need to give it some velocity on the final velocity. So what am I doing when I do this? Think about the final velocity, switching back to my diagram, as the hypotenuse, right? This is not just the velocity, but it also equals, right, the hypotenuse. This is hypotenuse, right? And I have two components. I have this is my y component, right? And this is my x component, right? But I don't know, sorry for the arrows, but I don't know what they are, right? Because I wouldn't know how fast I'm throwing a ball typically if I'm putting it up into the air. I don't know what my x component is, right? So I want to derive, I have my total velocity, I have my hypotenuse, and I want to find the x component and the y component. But I have my hypotenuse and an angle, right? Going back to trigonometry, that's where we can use v cos theta, v sine theta, which we actually studied the first day, right? So, going back to the code for a second, that's what we want. So let's assign a value, which is going to give our total velocity of 5, some kind of value, right? We don't know what it's going to be. What would you say the angle should be? Well, if we want the farthest distance, remember we talked about this, the angle should be 45 degrees. So if I was strategic, if I was standing on a hill, and if I can calculate about 45 degrees, I want to get as far as I can based on my muzzle velocity, right? I want to go about 45 degrees, right? If I want to go shallow, if I want to kind of hit a little bit closer, then I could bring my gun up or my cannon a little bit up higher, and it would be higher up in the air, but closer in, right? With the same velocity, okay? All things being equal. So let's put an angle here of 45 degrees, right? So we have an angle of 45 degrees, a total velocity of 5, and we want to find the velocity y and the velocity x. Hey, curious, can we use these same equations here, right? For the position y and position x. Have they changed? And actually, if we look, I look down at the second situation, right, which is this one, and I start looking at, this is the first one for finding the components to velocity, but the second one looks, well, depending on what we want to find. Here, we're actually finding the time it takes to travel from one place to the other, right? So we have time because guess what? Our time is being calculated. We're not calculating the total time yet, right? Because, you know, that's one thing we can find. And we're going to get some kind of problems that they're going to ask for this. But what else can it do? To describe the motion, look what it gives us, right? It almost has the same kind of this parabolic motion, right? And it's almost like I can use the exact same equation that I used before, right? Now, if I want to find the total height, I can use this equation here, derived from equation number 11, right? But if I actually want to define the motion, this parabolic motion in situation number 2, standing at the ground, right? I can use the exact same stuff that I already have. And if you notice, it already did that motion from the top of the hill or the cliff. So I can use both these two equations still. All we're doing is we're just compartmentalizing the velocity. We're calculating the velocity y and velocity x instead of assigning the velocity y and velocity x. We have a total velocity across the, you know, kind of the hypotenuse, and we're just finding the velocity y and the velocity x. That's what we're doing. Okay. So this is the second situation. Okay, let's try this out and see if it works. What we will do is inside Unity, I want to bring the ball down just above the ground. So kind of, here's the ball. I want to bring it just above the ground, just a frame select so you can see that it's not quite at the ground, because if I bring it too close, then it's going to not work, right? And I'm giving it some kind of kicking velocity here. So let's see what happens when I do that. So, whoa, right? And that was 5 meters per second at an angle of 45 degrees, okay? If I give it more velocity, initial velocity, more muzzle velocity this way, right? It's going to go farther, right? With the same angle and higher, okay? Why? Because when you think about what we're doing, we're taking out some portion of the angle, right? Some portion of the velocity, the initial velocity, right? So if I say the velocity is 10, let's put 10 in there instead of 5. So go back and change the velocity. Instead of from 5, we'll make it 10. Then it should go twice the distance and twice the height, right? 10 velocity, right? However, if the velocity is 10, how do I figure out what the velocity of the y component is or the x component? How do I find those, right? V cos theta, V sine theta, x and y. What is V cos theta of 45 degrees if V is 10? Well, cos of 45 degrees is 0.707, right? And sine of 45 degrees is 0.707. So if it's 10, right, if my velocity is 10, that means I'm moving 7 this way and 7 up, right, initially. Minus gravity, I'm going to get that parabola. I'm going to get that parabolic arc that I'm getting, right? Gravity is the thing that's pulling me down, okay? So it gives us this natural motion. 10 in our game, in our situation, our simulation is too fast, right, for me to do that. Some value of 10. Now, if you want to change the scale again, we can do that. By changing our scale, we can say that our UPM right now is 4, so 4 meters per unit. So how many units per meter? 4. 4 units per meter. 4 unity units per meter, right? If I increase that, let's say to 8 or 10 itself, let's make it 8. It's going to be double the scale. It's going to be half as fast, right? And you can see that again, I'm going to get the same thing that I did with when my velocity was only 5, right? Which is a shallow kick. Let's see if that worked. Did I actually save it? I did not. But this 8 units per meter, right, as an example with a velocity of 10, you can see that it's going to be dividing this one plus the negative 9.8, right? So it gives me a different scale. I'm not changing. To this moment, I have never changed my frames per second, how many frames I get every second. I'm keeping it consistently at 50, right? And I'm dividing everything to give me that second every second, right?
Now, if you had a trillion things on the screen, it would start stuttering, or would that fixed update?
Fixed update, what it does, remember there's 3 types of updates in Unity. There's update, fixed update, late update, right? Those are the three updates that Unity provides you, right? Fixed update, whenever I think about fixed update, I always think for physics. Right? Whenever I use physics, any kind of physics motion or physics simulation, I use fixed update and fixed delta time, right? If I use a regular motion, non-physics based, like some kind of other motion or some other thing I want to do, some other update, some kind of redraw that have nothing to do with physics, I use update. Okay? All right, so that's the second kind of motion, right? This cannon kind of motion. And now I'm figuring out, the velocity. But what if, I'm just putting it out there, right? Remember this other type of motion also gives us the ability to see other options here. Notice that we can try and calculate the height. What's the total height of this option? How do I figure this out? Well, depending on where I start off, right? If the question asked you on the test, for you to calculate it on the test, given that you have an angle of 45 degrees with an initial velocity of 10 meters per second, right? What's the highest point of the arc of the projectile? What is the zenith? What happens to the projectile? What is the highest point the projectile reaches before it falls back to the ground, right? Well, then we use this equation here. H, the height, is equal to the initial velocity squared. So let's say if it was 10, it'd be 100, right? Times sine of theta squared. So 0.707 times 0.707, right? That's what it would be. Right, and then divided by 2g, which would be negative 19.6. And then you have the total height, whatever. That's how you can figure out the height. So these are really interesting, good equations. And again, on your test, I'm going to give you a bunch of formula sheet. I have to correct myself. Logan corrected me. It was a formula sheet, sir. That's what he said, right? It wasn't a goddamn cheat sheet. You tricked us, right? I didn't trick anybody. But I always call it a cheat sheet because when I was doing calculus and physics back in the day, there was no formula sheet. No, there was nothing. We got nothing, right? But anyways, it doesn't matter. That was back in the day, and now they do things differently. We have the internet. We're more realistic when we have some kind of data in front of us, and it's hard enough to figure out the problem with the formulas, right? How to break down a problem. right? But what if you're given, so there's two possibilities here. This is one, we can find the height, and we also can go back and to this one, we can find the time. So let's say, for example, we don't have the time, but we have the velocity and we have the angle. We can find the total time it takes to travel from A all the way to C, right? So from the beginning where it starts off, how long will it take to travel to the end? Now, in our games, how often do we need to know that? How often do we need to know exactly how long, how many frames it's going to take to get to the other side, right? We may not know or need to know that, but it's nice to know sometimes or project or interpolate where an object is going to be, especially when it comes to bullets. And the reason for this is because bullets, it's a classic problem, they tunnel through objects, especially if they're moving fast, right? Small object tunneling through some kind of block. Every frame, it's going to move a certain amount of distance, right? There's going to be, if it's really fast moving, and if it's a really small object, it's going to tunnel right through, and you're not going to see any kind of collision, right? Because our collision algorithm is going to miss. It's going to say, where am I? Am I colliding? No. I'm past it now. Where am I? Am I colliding? No, right? So I haven't collided either before or after, and I've tunneled right through, right? However, there's ways of interpolating. I'm saying, where am I going to be next frame? That's a different question, and that's what we use some of this physics stuff for. Okay, so time, and we can also find the total range. What's the total distance that it's going to travel, given the data we have? So, for example, if I want to find the total range, I can use this equation here: v squared sine 2 theta, right? So if I looked at, instead of 45, I put in 90, right, and I multiply it by v squared. What's sine of 90? Give an example. What? Right, sine of 90 is 0, right? Times v squared, right? That's kind of weird, right? If my sine is 90, and if you plug this stuff in and you're looking at it going, wait a minute, if my angle is 45 degrees, sine of 2 theta, theta being 45 degrees is 90, multiplied by v squared over g, right? The whole thing will be 0. That doesn't make any sense, right? That's our total range. But what if it's another angle? What if it's not 45? What if it's something else, like 60, right? So 60 and 60 is 120. Plug that into your sine function. So if I pull that up, if I say calculator, let's say, for example, it was 60 degrees. So I said, 60 would be 120. And I use my sine function, right? 120.866, right? And then multiply it by, let's say our initial velocity was 10. So 10 times 10 is 100, right? Equals 86 divided by gravity, right? 9.8, right? Would be 8.83, right? Meters, roughly, with 10 meters per second, right? With an angle of 60 degrees, right? That's so you can find out the total distance, the range of an object. And how does this make sense? Well, I want to find the distance, how fast it's going to travel. Why would I want that in physics or in game? Again, for the same reason. I want to know if my enemy is going to be hit. Am I hitting my wall? Am I hitting my enemy? Am I fast enough? And I can already interpolate where the bullet's going to be, right? Before I actually launch the bullet. I know where it's going to be. So I can do my calculation, especially on an immovable object like a wall. My wall is not moving. I fire my bullet. Is it going to hit? Yes. Do the collision, right? If it's not going to hit, don't even bother. Okay? The third type of motion that we're going to handle is this. We already kind of handled it, right? Where I'm at the top of a wall and I have an angle, right? But instead of having both the x and the y components separately, I just have the initial velocity, right? Plus an angle, which is this situation, almost like an extension of 2, right? In fact, you can use number 1 and number 2, the first type and the second type, and derive the third type, right? How does this work? I already have it, right? All I have to do is raise this up to here, right, to simulate it. So I can put it up to here. Let's say I'm at the top of a cliff, and I charge it up. I have some 45 degrees, and it goes, whoo, right? And if I lower the speed, just to make it so that's more something we can see, right? Let's make this, instead of velocity of 10, we'll lower that to 5, right? There's a velocity of 5. With a UPM of 8 and a FPS of 50, right? Our angle is 45 degrees for now. We'll change that angle in a second, just to show you the type of simulation we can do. So I've halved the speed, right? And you can see that the motion is going to be kind of down. Same thing we talked about before. So now we're figuring out the position of the object every frame. And we're redrawing it every frame. That's what Unity does too. It clears your canvas, right? Whatever you see here, and redraws every time. It kind of re-renders or renders the object every frame. Okay. And if I was to make it a much maybe a shallower angle instead of the angle that I'm making it, I made it 45. Let's chop this angle down to, or let's make it so it's going to go higher up, but not as far. I can make it 60, right? 60 degrees. And you can see that the angle is going to be, when I try my simulation, it's going to be a lot shallower. So it's not going to go as far, right? Especially if I change to something else. So if I say instead of 60, let's make it so that it is 75. Let's see if I see more of a dramatic thing there. So 75. Unity was crashing on me hard last time I got together. There we go. There's 75. See that? So it kind of went up a little bit higher and then came down. And if I can vary that, and if I made it 90, if I change this to 90, what should happen is it should go straight up and straight down onto the area that I am. It's almost like I'm throwing it up in the air and it's coming down again. Okay. Let's try that. So 90 degrees, an angle of 90. It's going to go up and go straight down again, right? That's an angle of 90. So then that's how the angles work. That's how those three types of motion are you're going to see, right? Now, how do you handle some of those equations? So sometimes what we want to find is the total distance or the range, right? But we know that we have a parabolic arc, right? That it's starting off the top of the hill. So we can find the total range like normal. And then, so that's the first type of problem, right? And then we can say, well, or sorry, that's problem number 2, which is the parabolic arc. And then the second type is, what happens if we drop it now with a velocity? That's the second type. It's almost like we're taking one part and adding it. We can break this problem down into 2 parts. All right, so we want to find the total distance, right? The total distance here. We have h. We have the height of the object, right? And we want to find r, right? So what we can do is we can add. If we want to find the total time, we do this. But if we want to find the, if we have the height, that's the total height that it's going to fall from here to there, and we have this equation. We actually add sine theta in there. We can calculate the velocity if you want, right? If we have the height, we knew have the height because normally we have a height here, like 50 meters or whatever it's going to give you, right? But if you want to find the time, and this is what I talked about last time, it is like looking at the quadratic equation because you have 3 terms. And remember the quadratic equation is ax squared plus bx plus c. We talked about this last week maybe or the week before, right? Ax squared plus bx plus c. And we want to derive our time value, right? So we're going to say the first term is this part. So this is A. This is B, not including the T. If I can actually highlight it. I can't. This is B. And this is C, right? So H is C, V sine theta is B, and 1/2 G is A. And if you take those values, if you actually write them down, A is this, B is this, C is this, and then sub it into your equation here, where T is the final time value. And we will always want to get a positive value out of this, just like we did last time, because time is positive, right? Because from 0, it doesn't march backwards, typically. And once we've done this, we go minus B plus or minus the B squared minus 4AC over 2A. We can find the time, and that's the hardest type of equation that I'll give you. There might be another part on the test where you might see here, given this information, how long does it take for it to hit the ground? That's what you'll be given. So you'll be given the height, in this particular case. You'll be given the velocity and the angle, those 3 things. If you don't have one of those things, you can't figure out the time so easily. You have to use another equation to figure out the time, right? All right, so that's really the third situation. And here, we're just giving you additional equations to make life easier, okay, by just switching things around. Like, for example, we're looking at taking equation number 4, number 8, and number 4. We can get something else. If we want to find the angle, we can do the same thing, right? We can get the angle by taking these two equations, right? We know that if I want to find the theta, I can get the angle. I can use the inverse tangent or the arc tangent, that's what it is, of Vy over Vx. So the initial velocity on the y-axis and the initial velocity on the x-axis, I can find this. And to prove this to you, we can do this in code too, right? We can say that theta is arctan, right? Usually it's arctan or inverse tan. And in our code, just to show you, I'm not going to do it, but you can see that MathF has quite a bit of, I think it's atan. There it is. Atan2 is actually the one you want to use. Atan2, right? Atan2 is arctangent, right? Which is the inverse tangent. And we plug in the ratio of the velocity of the on the y-axis over the velocity of the initial velocity on the x-axis, those two things. If you have those numbers, right? And then you can find the angle of attack, right? Sometimes you need to find that as well. When do we need to find that? When I don't know, I want to find my direction sometimes. Sometimes I want to say, where's my gun pointing? I have a gun and it's pointing up at a certain angle, right? I don't know what that angle is, right? But I need to point it up. I don't know what, I have my velocity, right? I have my other components, my velocity on the x and velocity on the y, right? But I don't know my angle is. I don't know what my angle has to be, you know, to accomplish a certain, to go a certain distance. So from a programmer's perspective, when you get the question that I'm going to give you on your assignment number 2, you're going to get a programming question that you and maybe 2 of your compatriots, your colleagues, you and two of your people, maybe 3 if Logan convinces me with a campaign, right? The campaign is saying we want 4. Well, let's say you and 2 for now, right? You're going to get some basic questions like the ones in the back of this PowerPoint. Now, the PowerPoint actually that I put up online gives you some more data in terms of how to use vector syntax. When you get your assignments, I'm not going to give you vector syntax like this. I'm going to give you my syntax for the first 3 situations. I only want you to know the first 3 situations for 2D motion. Okay? So let's look at that. Notice that we did some of these, right? But at the back, I want you to kind of see something. There is the book gives you a little bit of help to try and figure out how to do questions. One of them is, they say is, first you conceptualize. Okay, so let's draw it out, right? Then you try and categorize. Which type of situation is this? Is this situation number 1, number 2, or number 3, right, in general, right? And then you start, you know, writing down your initial velocity, all the known variables that you write down, right? And once you do that, once you figure out the variables, you calculate the math and you finalize your answers. Okay. I'm not going to talk about this. We already talked about. We're not also uniform circular motion, although it's mentioned in the PowerPoint. I'm not covering right now. Okay, I'm going to cover circular motion later on. Okay, we're going to refer back to this PowerPoint later. And same thing with tangential acceleration. I'm not going to talk about it too much. We're going to talk about it in circular motion. Okay.
Like car swerving motion?
Kind of, and also things like tangential acceleration would be something like when you're on a roller coaster and there's an acceleration. As you're going on a roller coaster, there's circular or circular motion that's accelerating you down towards the middle of the kind of the radius of whatever the angle is going to be, right? So we're not going to cover this right now. We're going to cover it later. But what I want you to look at for your while you're waiting for my assignment to come out is this. There's some problem starting off at page 72 of your PowerPoint, which is a water balloon is thrown horizontally with a speed of, V naught is what it is, 8.31 meters per second off of a roof, right? Of a building of a height of 23 meters. How far does the balloon travel horizontally before striking the ground? First of all, what kind of situation is this? Is this situation number 1, number 2, or number 3? Which one? That's the first thing you have to ask yourself. So it's thrown horizontally, right? With the speed of something. So that means I have velocity across the x-axis but no velocity across the y-axis. That's what it means. Okay. Okay, and I'm not given the total velocity. I'm given one component of the velocity. So it's definitely not, equation number 2. It's probably situation number 1, right? Why? Because I've only given one component of the velocity, right? I don't have the total velocity. It didn't say in here that my velocity across, my total velocity, my muzzle velocity is x. It's giving me my velocity across the x-axis. When I see that, it's the first type of motion, all right? Second thing is I'm given the height. So I'm going to use that equation. Because my x, I have those two equations, number 1 and number 2, which I've already programmed into your code here, right? If I go back to the code, these two position equations, position y and position x, are the equations that I'm going to use for this one, right? Same as I used every other time, right? But instead of having a total velocity, I only have one component. So I'm going to go back to what I did initially, where I don't have my total velocity to figure out my velocity, right? And I would plug it right in here. Now, if you're a good tooling person, right, I've hard-coded my values here, right? I've made them all private. You can make them public on your inspector, and you can plug in some values, plug in your values there, and it can calculate the motion for you. And if you really are smart, you can actually output the final, the final position before it even gets there, and in another variable, and that's going to be your assignment. Take some of this stuff here, and then calculate the final position before you even press the button. And there might be a button on the screen. Press the button, fires the object, and you can actually maybe with some tooling set with some kind of other user interface, a slider or something, set the speed and the angle, right? Where you can actually change the angle. It actually change the angle of the object. Okay. Okay, very simple stuff. So that's this. That's what this is going to do for you. So that's the one type of question you're going to get. So think about this. Water balloon is thrown. That means that my VXT is 8.31 times T, right? Now it says the water balloon is thrown horizontally. How far does it go before striking the ground? Okay, cool. I don't have T, right? I don't know how long I have, right? So I'm missing some components to this, right? Okay, but it's 23 meters. I have that little piece of data, right? Which means my total distance across the y-axis, right, is 23. So if I was to drop it, I know that the first equation, which is v naught, vy, which is 0, t, right, is equal to 1/2 at squared. I know that, right? And if I take 1/2 at squared, and I know that whatever 1/2 at squared is equal to 23, right? Think about this. Let's write it out with my little tablet, right? If I can. By the way, I would have loved to do this with my iPad, but it is what it is. So let's suppose that I have this situation. I'm on the top of a cliff, right? So we're going to draw the cliff here, right? And the top of this cliff is approximately 23 meters, right? That's what we've been given. We've also been given a V on the x-axis of some value, right? And if you look at the value we've been given, 8.31 across the x-axis. So here's 8.31 meters. So we write down this stuff here. And we've also know that V on the y-axis is equal to 0. We know that, right? Meters per second. And we also know that, so x and y, and we also know that G, right, is equal to a negative 9.8 meters per second, okay? We know these things. But what it's asking us for is not for these things. It's asking us for how far does it go before we're striking the ground, right? How far? And that's the range. But I don't have time. So is there some kind of equation that I can use from the first situation where I don't need time, but I have this information to find the total distance and this information, the height, right? Yeah, let's take a look. So if we go back up to here to the first situation, right? And I'm going to stop this now, right? In a second, guys, just bear with me one more second. Well, I can't use this one. 1 and 2 need time, right? I mean, I could find time because I know the distance is 23. So I could plug 23 in there and say 1/2 a. So where time squared is equal to 23 divided by half a, right? I could do that. That's t squared. That means time can have two values. T squared means that you can be one value or the other value. We know that it can't be a negative value, right? But t will be the square root of whatever the value is, right? That this 23 over a. And if I did that, if I said, well, it's 23 meters divided by half g, which is negative 4.9, right? As I say, which is roughly negative 4.69. Can I have a negative square root? Because t squared is equal to negative square root. So we're going to have to take the absolute value of this, right? So let's just say negative, so 4.694, 4.694. So let's do that. 4.694. We're going to take the square root of that, and we're going to get roughly 2 seconds. That's how long it's going to take for it to fall. Does that make sense? Let's see. If I take 2 times 2 is 4. 4 times half of 4.9, right? Right? So half, so 2, so 4 times 4.9. So 4 roughly times 4.9, right, is equal to some kind of, almost like 20. I didn't calculate exactly, but some kind of meters that makes sense. 23 meters. So it makes sense, right? So we know that the time, we can figure out the time. So again, to figure that out, I'm going to take 23 meters divided by 4.9, right, is equal to this value. I want to take the square root of that, and it's 2.16 seconds to go 23 meters. That's my time value. I got that so far, right? Now I just need to figure this out, right? So I take my initial velocity, which in the equation was 8.31 meters per second, right? 8.31 meters per second, and multiply it by time. So multiply this by 8.31 meters, which gives us a total distance of about 18 meters. All right, so to answer the question, the full answer to the question, if you look back down, and this is where I want you to practice some of this stuff, right? Again, starting at page number 72, I said, something like that, or 72, yeah. How far does the balloon travel horizontally between striking the ground? The balloon travels 18 meters before striking the ground, but you would show all your work. Here's my time. It takes 2 seconds to hit the ground, or whatever. Now that's one solution. The other one is, can you find an equation? Can you find an equation that doesn't need time? Well, here's one. We got velocity, right? The total velocity is the combined velocities. We can find that out. But we want the total distance, right? And we have another one we can use for total from A to C. But in this particular case, we don't have any upward motion. Well, that's okay, because we know that cos of theta, it's 0, right? Cos of 0 is 1, right? So our horizontal motion is 1. We can still use the same equation, right? We just have to say that, well, whatever the velocity is, instead of v cos theta is 1 or 0, right? So we can, once we have that information, we know we can find the time from that, right? How long it takes to go from A to C. We can figure that out. And then we can plug the time back into, again, back into the original equation, right? The Vxt equation. We can also use this equation. We have the initial velocity, the total velocity, which we can find from adding the two velocities together. We know that the y velocity is 0, right? So we can find this velocity out. And then we can take, this is the total velocity, by the way, so the hypotenuse, multiplied by some sine theta. We don't know what sine theta is, but we can find that out too if we really want to. And then divided by 2g. But this is a lot of work for us to find out. And I think the first approach that we used is the right approach. Okay? Because we don't know what the angle of attack is. Any questions around this first type of question? Please take a look at the ones in the back. I will have the questions that you're going to get are very similar to this, that you're going to see this kind of stuff. Yes, Emma?
My other question is, why does time need to be set?
Oh, down here you mean inside my script? Well, the reason why I reset the time down here, right, where if it's on the ground, that way if I lift it up, it's like I'm saying, okay, start my physics simulation from here now. So wherever I drop it, that's where the physics simulation starts again, right? So my new position. Otherwise, what happens is time will continue on. Like the time function will keep calculating, keep adding frames forever and ever and ever, right? I don't want that. I want it to only accumulate. I want to only do the physics stuff when I'm doing physics, when I'm dropping something, or when I'm throwing something. Okay?
So that's because it's with the countries that you're making?
Yes. Yeah. Any other questions around this stuff? All right. So this video, which is very long, is going to be up on YouTube for you guys. Hopefully this will help with some of the stuff we talked about today, and it's going to help you with your assignment number 2. Okay? I hope to see you guys next week. If I don't, I'll see you when I see you, right? Let me just stop my video. Hold on a second. Let me stop my video.